So they have a microphone.
Start calling you Mr. Retraction.
Similar to it doesn't make a high pressure so so if you can look over this portion, check this.
Well, I think it's probably not a shelter, but it's sort of like a and there's signs, see little signs in big places. You know, when you get north of like North Berry, and they're going to have some of their irrigation, but they had a big dedication there. Good try. Yeah, there's a lot of them. They're running with their company. You know, like here's the
would never. Why would it?
That's one of the funny things. I remember my dad using them all the time. Go right up and turn that.
You have tickets?
They just went
It's in my list of things too.
They did everything from last.
Too close for them. Sit over there. Yeah, too close to the screen.
Well, two of them did make it to the boom later on. Yeah, like the idea of politics was potentially. The way it was set up, you know, like, they couldn't have, they really couldn't have landed that kind of
For Matt's benefit, I'll do a sound check to see if you can hear. Hard to know.
Got a delay.
We're testing a new microphone this evening to see if our broadcast works a little better. Apparently the sound quality in here has been not bad, but it's the one that goes into the camera that has been problematic as well. So we'll just see if that's working.
Finally got it.
Okay, so it seems like it's good. Well, welcome to our meeting this evening. This is the Royal Astronomical Society of Canada Victoria Centre. I'm Chris Purse, the Centre President. I'd like to welcome everybody here this evening. On our agenda this evening, we have a few things. I don't know if anybody has anything that they would like to announce from observing. We'll have some announcements. We'll have our guest speaker, and then afterwards we have coffee and tea in the Elliott Building, 4th floor lounge. If you'd like to join us, everybody is welcome. If anybody is visiting this evening, we do have complimentary copies of Sky News magazine. So feel free to help yourself to one of those. I also have the calendars that were pre-ordered. So if you would like to pick up a calendar and you've ordered one, please let me know, and we can take care of that. I'm also taking orders for the annual general meeting dinner, which will be in November. So if you would like to attend that and you haven't already told me about that, please do so tonight or at Astro Cafe in one of the coming weeks. So maybe I'll just mention some events coming up right now before we go into the announcements. We have our Victoria Centre Observatory taking place on Saturday evenings at this time of the year. You do need to be on the active observers list to participate in that. Astro Cafe is back in session until the end of May, with a few breaks here and there, probably, but please come out to that if you're available. We have a concert, and Jim has tickets with him now, and maybe I'll invite him to say a few words. Our center is involved, and we've been given a special projects grant to help with this concert, and it's the day before our annual general meeting, so we can have a real astronomy weekend in mid-November.
Well, you've pretty much said everything that needs to be said, but David Lee, John McDonald, and I have been working with the Christchurch Cathedral music program and the two lead musicians, Michael Jarvis and Paul Lutchkow, who put on the chamber music concert in January of 2017. This will involve a small orchestra, all playing on period instruments, music by William Herschel that is extremely rarely played. It will be symphonies, and there's an organ piece which they rediscovered. It had been misfiled in the British Library, and it is part of the RASC 150th celebration. So we hope very much that members of the club will come out and support it. The tickets are $30. And I do have tickets with me tonight. David Lee also has a set of tickets. He'll be at Astro Cafe. You can buy them online at Ticket Rocket. If you buy them from us, you don't pay the small service charge. But it should be a really fun evening. And I might also mention students can get in for $5 on the night of the concert. So if you have grandchildren or children who are students that you want to bring and come to enjoy, this is extremely accessible, fun, pleasant music. So it should be a wonderful evening, and hope people in the center will come out and support it. And I will have the tickets. I have the tickets for anybody who wants to go.
Well, thank you, Jim. Okay, so on with the announcements. So the current membership is in the upper 270s, I think 277 when I checked yesterday. So we seem to be holding our numbers fairly well. I don't think there's anything else to report other than we are going now into a time of electing a new council for the center for the next year and probably 2 years. So it is customary in the center that you do a position for a year and probably extend it for a second year. And we're at one of those turnover times where most of the current members have been in their position for at least 2 years, if not longer. So Sherry Butner, our past president, is busy working on a new slate, and we are short some nominations from the existing council, so there are some vacancies. So this would be a good time to consider putting your name forward if you'd like to join the council. And that takes place, that vote or that council starts after the AGM in November. So I just mentioned that because, so you'll see some information about that. And I've found in the time I've been involved, having been both the previous second vice president and now president, it's not a huge time commitment. I mean, every now and then some things, there's a flurry of, but a lot of it's done by email. And there are generally about 5 council meetings in a year. So the way it works out. So it is not a huge time commitment for most of the positions. And we need that. We need people doing those things. So if you feel you have the time and the inclination, we'd really appreciate seeing some new faces on council. Okay. Our Vice President and Sky News Editor, Reg.
Hello, good people. Before I start, I should introduce some people who occasionally come. Claire and Dave drove all the way down from Manus to join us. And we also have, where did he go? Dave Cooper. Oh, there you are. Yeah, Dave Cooper came all the way from Calgary to attend our. And there are some old timers in the back that I will not identify, but it's great to see them at the meeting as well. The October issue of Sky News has got, besides the president's message, it has an album of photos taken by our youngest member, Nathan, using just an iPhone, and he just handheld it over his eyepiece. It's quite amazing what Nathan has done. We also have an article on Martian dust storms to learn about how they're kind of produced and what's the most favorable conditions for that. But most importantly, the editorial board got together and decided to aggressively promote the Herschel concert, which details of which are on page 10 of this wonderful publication. And I have a limited number of hard copies. If one would, anyone would like one, please see me at the end of the show.
Okay. Thank you, Reg. Deb, anything from?
Nothing to report.
Joe, secretary website, anything newsworthy? Okay, great. Bruce, our treasurer's report.
Currently, our members account stands at $14,259. Our gaming account still at $20, being kind of unused these days due to the lack of wanting to inflict raffles on the general populace. There's so much fun. We're just doing the year-end stuff right now for the Victoria Center, so it's a bit of paperwork shuffling around. That's where we're at now, and I might not be here this term. So I'm quite happy about that after 6 years-ish of being treasurer, so that's kind of nice. We want something else.
We shouldn't count you out yet.
I feel pretty counted out. And we've been spending money like drunken sailor lately, which is really good because we've also been bringing in. That's kind of what we want to happen. We have people now that we've passed that AGM phase of basically Scrooge. Now that we've got people back to actually spending money for things we actually need, it's a really good time right now to get the funds moving out for projects, things like the little fuzzy creature on top of that camera. We get done, so lots of good stuff happening.
Thank you, Bruce. And maybe could the council have a quick meeting down here after the speaker to conduct one item of business to approve a new signatory on the bank account? You want to do that, Senior? You've got the paperwork?
I do not.
Perfect. Thank you. Okay, Outreach Coordinator Ken.
Nothing much to report. I would like to thank all the people who participated in the outreach this year. I really appreciate it. And I have lots more jalapenos than I need, so please grab some jalapenos.
We've become the Pepper Club as well. Thank you, Ken. Sid, schools program is underway, I guess.
We are back on line with the school program. We have so far 33 reservations have already made for the 3 school districts. And tomorrow we are going to, Diane is going to help, going to Georgia for 2 presentations. So yeah, it's going to be very busy time again this year. I do need help for night sky viewing on November 15th. And 16th is going to be conflict with Jim's concert, but somehow we will manage. So if you would like to help on the 15th and or 16th, please let me know. Thank you.
It's going to be a busy few days, Sid.
Yeah.
Thank you. I don't see Nelson with us this evening. Chris, do you have anything to say? For those people who don't know, by the way, Chris Gaynor is the national president of our association, so we're lucky to have the president of the overall society here with us this evening.
Yeah, so you're not national.
See him.
Yeah, I can't think of anything really exciting. We have 1 or 2 in-person board meetings, so I'm going to call, we could for that, and we're just, we've got quite a heavy agenda, and I think something that happened a few weeks ago is kind of important. Well, we got a new treasurer, and Catherine Carr from Coronal, who's been doing a great job. And crunching numbers, and earlier this year, it looked like we were waiting for some scary numbers in terms of our deficit and all this. Well, it actually doesn't look so bad now, and one reason for that is, we've engaged a fundraiser, and that has been bearing some fruit. So we are in fairly good shape in terms of our budget in general. We are going to have some challenges ahead. We're going to have to look at the financial situation around the other Sky News, not the Sky News we know and love here, but we're going to start talking that at our in-person meeting. And yes, and the only other thing I would say is, we just heard from the Governor General a few days ago. We got the patronage to the Governor General and our greetings on our 150th anniversary. When we got one from the last Governor General, patronage, but every time he changes over, we have to go and ask for it again. Fortunately, we don't have to do that with our oil thing. But, and then of course, next year, and it's not really a problem with this, our General Assembly is going to be in Coronal. And it's going to be a meeting in association with the American Association of Variable Star Observers. So, if you agree to that, and I know there are some people here who are, this is going to be a fun meeting. So that's all I have to see right now.
Thank you, Chris. Matt, anything from the technical side?
Well, we have been spending money. Thank you for noticing. We have a beautiful dead cat. No, so the audio should be much better for this meeting. Everybody check your email, give it a listen, give me a review, 5 stars. Point of personal pride, we finally have a cover over top of the sprocket box at the observatory. Thank you, Dan, leading that project. As well, we have a focus mask. There's going to be some alterations made to it. It's a batten-off mask, same as before. It's bigger size. It's meant for a smaller, bigger size. So we're going to make a slight alteration.
Apparently our 16-inch telescope.
16-inch is not 16-inch.
It is not a standard 16-inch.
Okay. This is the thing. Apparently also for our flat field panel, very disappointedly, we're going to have to send you back a bunch of that money because I'll be returning. So that'll be a mess. Anyway, I'll sort that out. Things are taking long. Come out and see the stars.
Yeah. Thank you. Yes. And Michelle's not here this evening. So anything else from the floor?
Well,
yeah.
Just wondering how we are on the camera, where we're at on the PCO cameras.
Haven't picked out a winner yet.
The search continues. The QSI, if not everybody is in the loop, has died and is not fixable. So we sent that down to Quantum Scientific Imaging and they weren't able to repair it.
It's now in the UK somewhere. We're not getting it back.
Yes. Unfortunately, the company sold and the new company doesn't
The
have any
original
parts.
company sold, the new company didn't buy the part of the company that involves repairing the things that the company makes. Go figure.
Yeah. So anyways, we ended up with a rather nice camera that doesn't work anymore, which is unfortunate, but we got quite a few years out of it. It was a good camera. It would have been nice to keep it running longer. I'll just put the upcoming events list back up again. And just a reminder, if you had wanted a calendar, they have arrived. If you're interested in going to the AGM, please see me or email me at some point, or the dinner part portion, and let me know your meal choice. If you're interested in a concert, see Jim for tickets. And I think that's it, except that could I see the council members after the talk so we can pass this one item of business. Over to Reg.
Our speaker tonight, Dr. Rico Winslow, I've been in contact with her. Email started way back in March, and I've really been looking forward to the presentation tonight. But you'll be interested to know that Rika was a member of the Royal Astronomical Society in Kelowna, where she grew up. And then she moved to UBC, and she had the good fortune in her undergrad working in degree in physics and astronomy to work with Dr. J.D. Matthews, and many of you will have known him. And he was involved with a satellite called MOST, which he calls actually the Hubble Space Telescope. So she did her undergraduate work with Jamie. And then she went and got a PhD at UBC in geophysics. And she specialized in space science and planetary science, and in particular studied planetary magnetospheres, and I learned an awful lot about how magnetic fields work and how they work in the sun and this sort of stuff. And as you all know, plasma is a lot more complicated than our regular planetary atmosphere, so it's a mind-boggling thing, and it's really great fortune that we have a person who understands all of this and will explain it all to us tonight. She worked on her PhD analyzing data from the Messenger satellite, which went into orbit around Mercury. And so Rika will explain some of her findings there. And also, well, she will be talking about coronal mass ejections and all sorts of things. So I'm really glad that we finally got Rika here. I should mention that she is with the University of New Hampshire, but at the moment she's working remotely and living in Victoria, which is a nicer thing. So, okay.
Let's see, does this work? Can people hear me? Okay.
And Rika would like you to ask her questions throughout, so it's kind of an informal presentation.
I prefer less formal, rigid talks. In academia, we have too many very rigid talks, so it's good to ask questions. And please let me know if you can't hear me. I tend to be on the quieter side, so just let me know. Yeah, thanks very much for having me here, for inviting me to give a talk. I actually used to be a RASC member when I was a teenager in Coronal, so it's nice to be back in this setting.
Turn off those chalkboard lights.
So yeah, my work focuses on different plasma environments in our solar system. Anything from coronal mass ejections to how coronal mass ejections travel and propagate in our solar system, how they interact with different planetary magnetospheres and interplanetary shocks. So that's what I'll just give a brief overview of my research and then focus on a few key aspects in a bit more detail. So I'll first talk about coronal mass ejections, what they are, how they affect different, what are their effects on planetary environments that we see. Then I'll highlight some of the key research that I'm doing on propagation of coronal mass ejections. So I'm going to say CMEs from now on to shorten it. And then I'll give you a brief overview of space weather, so how CMEs are affecting the planet Mercury, and then also how CMEs affect galactic cosmic rays, or GCRs, in our solar system. Now again, please feel free to ask questions throughout, so if some of this doesn't make sense, just ask away. So most of you, I'm sure, are familiar with large solar storms. These are what we call coronal mass ejections, or CMEs. They are large eruptions of magnetized plasma from the sun. They are observed in coronagraph observations, and they look something like this. Do we have a...
I didn't bring them.
Sweet, thank you.
I have a red one, I don't like those green ones.
Okay.
Sorry, Rich.
Excuse me.
No.
Yeah, there we go. So the images like this are obtained from Stereo and SOHO spacecraft that are showing the actual eruptions from the sun. Their speed, so these CMEs are, first of all, they vary with the solar cycle in terms of how many we get. So if you're in the solar cycle minimum, then about 3 per week. At maximum, we have about 4 per day. So these are quite variable, of course, in terms of how they propagate and come to Earth. That will, like how many you reach Earth, will also depend on the solar cycle. And also their speeds quite a bit vary with the solar cycle as well. So some of them can be ejected at a speed of about 200 kilometers a second, others at like 3,000 kilometers a second. So that makes a huge difference in terms of how fast they actually reach different planets. So up to coming to the Earth, the transit time can take anywhere from 1 to 4 days. So a lot of the research that's really key in my field right now is how to better forecast Earth. So can we get better at the actual timing? We're pretty good at this point in terms of being able to tell whether a CME is going to reach Earth at all, because we can see where it's being ejected from the sun, what latitude, longitude. But in terms of what time it's going to arrive at, we're only about 12 hours in terms of being accurate within 12 hours. So it's not bad, but we'd like to be able to do better. And so a lot of research is being done on that. And there are fairly large events in terms of the amount of mass that's expelled from the sun. It's about 10 to the 13 kilos. Of course, that's it's still a tenuous plasma, of course. And then a little bit of the anatomy of what a CME actually looks like. So it's made up of, because it's coming really fast, it's being ejected fast from the sun and traveling faster than the solar wind, it ends up forming a shock in front of the CME. So this, behind the shock, this is the shock here, and then there's a turbulent sheath, so essentially where the particles are compressed and heated, and here the magnetic field tends to be really variable. And behind the sheath is what's called the magnetic cloud portion, which is essentially a magnetic flux tube that's twisted up and anchored at the sun. So we tend to think of a coronal mass ejection as being anchored at the sun and just growing outwards from there. As it's expanding in the solar wind, it gets larger and larger as it's traveling. Now, of course, this is a cartoon image, and this is as simple as we can get, but reality is, of course, a lot more complex, and we can never fully observe exactly the full structure. But we tend to use models, of course, that are as simple as we can make them. Sometimes we can make them more complex, but sometimes the simplest models work best. So when we are trying to fit the observations, we tend to use these simple twisted flux tubes to model our CMEs. Now, just briefly, I'm going to mention what magnetic reconnection is, because that will play a bit of a role in my talk today. So magnetic reconnection is where field lines, magnetic field lines, essentially are broken and reconnected in opposite directions. So essentially, if you have oppositely directed magnetic field lines, they are able to reconnect and form, and at the same time release thermal energy. And so this reconnection process forms magnetic flux ropes throughout the heliosphere, some of them being the coronal mass ejection centers, so the magnetic portion occurs due to magnetic reconnection. And at the day side, magnetopause in magnetospheric physics. So I'll mention, we'll get to some of that as well in this talk. Now, I'm going to show a lot of data and a lot of observations throughout this talk because that's mostly my field of expertise. I work with a bunch of different spacecraft observations. So I would like to get all of us a bit familiar with what observations of a CME actually look like. So these are at the Earth. This is essentially what you would see if a CME passed by. So these are a lot of the observations I'll be talking about are magnetic field observations. So they're not pretty images, unfortunately. A lot of the times, I'm sure most of you deal with nice pictures of galaxies and planets, but I always just look at magnetic field data, so it's a little boring. Although I tend to like it because it's just 3 components and it's easy. Yeah. So this is the total magnetic field here, and then the 3 vector components, which is Vx, Vy, and Vz. We also have the temperature, and this is velocity and density. So these are plasma measurements. They're being made by different spacecraft. This particular one, I believe, is from the ACE spacecraft at L1, which is observing the solar wind continuously. And as a coronal mass ejection passes by, this is what it observes. So you see a large increase in the magnetic field component. You see a large increase in the temperature at the very beginning. So this bump here is essentially indicating a shock. This is the magnetic cloud portion of the CME. This part is the sheath where the magnetic field is highly variable, as you can see. And velocity is largely increased, of course, because it's much higher than the solar wind speed. And the density is very high in the sheath and just behind the shock, and then it goes down in the magnetic cloud portion. So these are some of the typical signatures that we look for when we're looking for a CME. And yes, as I mentioned, that the speed varies from about 300 kilometers to about 1,500 kilometers by the time it reaches Earth. So of course it has slowed down quite a bit due to being ejected into the solar wind and going through a bunch of drag. The magnetic ejecta portion, the magnetic field strength, is about 10 to 80 nanotesla, which you're going to see at Mercury when I show you CMEs there. They're much more strong. The magnetic field is much stronger. It can go up to 300 nanotesla in the CME. So this, the magnetic field in the CME goes down as well with propagation from the sun. So, of course, we get to the point of why should we care about CMEs at all? Well, they affect planetary space weather. They are time varying, so they cause different time varying conditions in the different magnetospheres of planets. So we've observed how they affect the ionosphere as far out as Mars. We see how they affect the magnetosphere of Mercury, and of course at Earth we have studied it for many, many years through many observations. And they, of course, CMEs and the shocks associated with CMEs can cause some of the largest energetic particle events in the inner heliosphere that are observed. So if we have, of course, astronauts out in space, that greatly matters to them if there are large energetic particle events. We'd like to know about those and warn astronauts before those happen. So at the Earth, we know that CMEs cause what are called geomagnetic storms. So it turns out that about 85% of geomagnetic storms are actually caused by CMEs. And so this connection between what we were observing geomagnetic storms at the Earth for a long time, but we didn't know what actually caused them. And so this connection between CME and the magnetic cloud portion of it causing the geomagnetic storm was made in the 1980s. So it's not that long ago, actually, that we've recently figured out that this is what's causing them. So I said 85% are caused by CMEs. The others are caused by interplanetary shocks, most of the time. And so what we care about with geomagnetic storms, of course, is that they cause large disruptions within our magnetosphere. They cause, of course, the aurora, but nowadays when we're so technologically reliant, they have huge effects on power grids, on communication systems, GPS systems, satellites. So we would like to be better able to warn, essentially to be able to forecast when they're going to come and better predict whether they will actually cause a storm or not. Right, so the main point that I'd like to make here is that whether a CME will cause a geomagnetic storm does not necessarily just depend on the speed of the CME or how high density it is or anything like that. The actual main point that will determine whether there will be an intense storm is if it has southward pointing magnetic component. So if the magnetic field has a southward pointed direction in it, inside the magnetic cloud, oops, this way. So in this portion here, if there is a southward component, meaning that it's below, it's negative, this BZ is negative, which it is in this particular case. And it lasts, for Earth, it usually depends, it has to be about longer than 3 hours and BZ has to be greater than -10 nanotesla. And if that's the case,
Can I ask a question about,
yes,
is this data taken by satellites or?
yes, yes. So this is taken by the A
As you
spacecraft.
said, it was near Earth, so
Yeah, so it's at the L1 location, it's the L
Okay.
Lagrangian point 1. And this particular spacecraft has been in operation for the last over 20 years, taking observations.
Just to clarify, you mentioned the Z component. Is that a radio component going from the sun to the Earth?
No, so X is the radial component
Okay.
in this coordinate system. So X is towards the sun, Y is essentially in the orbital direction, and Z is the north-south component. So that's why BZ is the one that we care about for having a southward component. That's the BZ component. And the reason that we care about it being southward is that the magnetic field, so this is Earth's magnetosphere. On the day side, here essentially, the magnetic field, as you can see, is pointed northward. So the Earth's magnetic field is pointed northward into the northern geographic equator. But if there's a southward pointing component in the interplanetary magnetic field, this white line here, then there will be a reconnection on the day side. That reconnection between the CME magnetic field and the planet's magnetic field allows energy, momentum, plasma to be transferred in from the CME into Earth's magnetosphere. That transfer of energy causes the geomagnetic storms. So this is why we care about which direction the magnetic field is pointed in.
So this reconnection process is important both at the sun
It's important throughout the heliosphere.
and at the Earth. Okay.
Reconnection accounts for a lot of different plasma processes. So definitely we care about it at the sun for actually causing the CME, then we care about it at the Earth in a different process, although, it's the same process, but in a different setting for it to cause geomagnetic storms, to transfer that energy into the Earth's magnetosphere. So that being said, the thing that we care most about is figuring out what the BZ direction is in the CME before it arrives at the Earth. And whether that BZ direction will actually stay in that configuration that it was when we first observed it. So, of course, this isn't very simple because it turns out that the CME changes quite a bit as it travels. So as it's traveling from the sun, it expands, first of all, because the decreasing solar wind pressure it is going to affect it. So as the CME is traveling, the solar wind around it is decreasing in pressure, and that allows the CME to expand outwards. So its radial size, for example, at Mercury is about 0.2 AU. By the time it reaches Earth, it's about 0.4 AU. So that's one way that it changes, but it also changes because it interacts with the solar wind and interacts with the interplanetary magnetic field. And because of that, it can rotate, it can deform, the magnetic field direction can change substantially. So even though we can say with fairly high certainty whether a CME is going to actually hit the Earth or not, we can't tell with very good certainty at all whether it will cause a geomagnetic storm. And that's a lot of my research comes into figuring out how to better predict this. So what I've tried to focus on is the fact that we have a lot of observations at many different locations in our solar system now. So this is really great because we can actually follow the CME as it's propagating from the sun outwards. So we have a lot of observations. Our messenger is no longer functioning, but for 4 years we had the data that we can mine. We had observations at Venus, which again no longer is functioning, Venus Express, but there are 8 years of data that we can mine here. We have, of course, a lot of different spacecrafts at the Earth. And we still have assets at Mars through MSL and MAVEN. So MSL is the Mars Curiosity rover. It does not have a magnetometer to measure the magnetic field, but it does have a radiation monitor, which helps. And there's MAVEN, which has a whole suite of instruments to measure the plasma environment. So a lot of my research focuses on putting together data from various spacecraft missions to actually follow the same CME as it propagates upward, and try and track it and study how it's going to change and rotate to better predict the magnetic field within it. So I'll show you one quick case study of a particular CME that was ejected from the sun in 2011, and it was observed in really good alignment between messenger and stereo. So stereo A is marked by this red dot here. That's one spacecraft. And then we had messenger here at Mercury. So you can see that if the CME was ejected essentially in this direction, it was clearly going to hit both, and then that's the case. So the CME was just ejected directly towards stereo A. So these are the observations that we had at messenger of this particular CME. And I'm not going to go into too much detail about all of the things that are in here, but the main thing, so this is again the total magnetic field strength, and these are radial, so it's similar to BX, BY, BZ. Point is that this BN is essentially the equivalent of BZ. So what you can see here, this is the shock of the CME when it arrives. This is the start of the magnetic ejecta, and this is the end of the CME. We had a bit of a data gap here, but it's still clear that there's a strong negative BZ or BN component, so a southward pointing component in that CME. Now, this is what we observe by the time we have by the time the CME arrives at stereo A. Now, we have a lot more observations at stereo A. We have a lot more data. Stereo has a lot more instruments that are useful for plasma observations. But the key thing to notice here, actually I'm just going to zoom in. This is the magnetic cloud portion of it. And what you can see is that the total, essentially the character of the magnetic field has changed substantially. There's a turbulent region which was not observed at Mercury. And there is, other than inside this turbulent region where the field is highly variable, outside of it, there is no negative component in the BZ or BN direction. So what we had observed, if we would have been at Mercury and said, hey, it looks like there's this CME that's going to come and hit stereo A, watch out, there will be a geomagnetic storm. It turns out by the time it would have reached stereo or Earth, there is no magnetic storm. So using observations that are far out in terms of distance from where we actually care about it, we have to be careful in being able to say what happens to the magnetic field on that distance. Essentially what had happened was that in the observations we figured out that there is something called a heliospheric plasma sheet or current sheet which happened to occur right before the CME hit. So I'm just going to skip this here, but show you essentially. So these are simulations of the steady state solar wind in the number density of the steady state solar wind. So this is the sun here, Mercury, Earth, and stereo A is over here. So what we care for this particular CME was Mercury and stereo A. And what this is showing are these high speed and high density streams in the solar wind that are essentially formed from the interaction of the slow solar wind with the fast solar wind. Now, when at these locations of high speed, high density solar wind, if the CME interacts with one of these, it can get distorted. So what we actually observed is that this particular snapshot is showing when the CME reached Mercury, and we see this high-speed stream having passed by Mercury just before. This particular snapshot is showing you when the CME is just reaching stereo A. And it shows that this high-speed stream occurred in between the time that the CME went from Mercury to stereoic. So we essentially crossed this high-speed stream with the CME. And by crossing it, the CME got significantly distorted.
Could you just explain the difference between a slow solar wind and a high-speed solar wind and what causes a high-speed solar wind?
So the speed of the solar wind, so the low solar wind speed is around 400 kilometers a second. The high-speed streams, high solar wind, is around 700 to 800 kilometers a second. And they're essentially formed in different regions of the sun. They come out of different areas of the sun. And when they interact, they can form what are called these co-rotating interaction regions, because they're co-rotating along with the sun. As the sun is rotating, they're tied in terms of magnetic field, it's tied to the sun. And so they're rotating around. And so these streams will just keep rotating around and around and around. And as they go around, they interact. The slow solar wind will catch up, the fast solar wind will catch up to the slow solar wind. And when that happens, it will form a shock. Essentially, there will be a fast forward shock in the front, and the slow solar wind will bunch up behind it, and so cause a higher density region. So these are essentially just continuously co-rotating with the sun. But what's interesting is that we didn't know that how CMEs interact with these, what will happen to the CMEs. We have never really observed it prior to this particular paper here. And so it's interesting to see, there are now, of course, models that are trying to figure out what is happening in terms of the actual interaction. But it's interesting to see that actually just interacting with the solar wind can substantially distort the CME and hinder our ability to forecast what will happen to that particular CME as it travels. So because this particular CME that we saw became a lot more complex and a lot more distorted by the time it reached stereo, we can hypothesize that CMEs may be a lot less complex closer to the sun. And so I don't know if you've seen in the news that Parker Solar Probe was recently launched and successfully launched. So this mission is going to go to the sun and essentially reach the solar corona. And in that case, we're hoping to get a lot more observations of how CMEs, what they're like that close to the sun, and try and propagate them out further from the sun. So I'll change gears a little bit now and talk about space weather at Mercury. So this is my other line of research. So first of all, why should we care about Mercury? One is that we had great observations by Messenger. So whenever you have great data from a spacecraft, that just says we should, of course, go and try and mine it as much as possible. But it's also interesting because it's the only other planet in the inner solar system that has a magnetic field, that has an intrinsic magnetic field. Which is pretty interesting for being the closest planet to the sun, the smallest planet, and still have a liquid core, because it has to have a liquid core in order to actually generate a global magnetic field. So I won't address that particular question as to why it has a liquid core, but my work is focusing on how Mercury and its magnetosphere respond to CMEs, and to CMEs on average, and also in particular cases. So before I go into that, I'm sure most of you know quite a bit about Mercury, since I heard that you recently observed Mercury's transit. Right? So that's really great. I've never done anything like that, by the way. I've worked on the Messenger mission, and Mercury was my PhD thesis, and I've never actually seen Mercury in a telescope. So, so maybe I'll have to come out to one of your observing nights.
You won't be able to invest.
No. I'm guessing it doesn't look quite like this. This is from Messenger, and that's a pretty nice shot. So it has Mercury has a radius of about 2,400 kilometers, so it's a pretty small planet. It's in a 3-2 spin-orbit resonance, which means that it has an 88-day orbital period and a 59-day rotation period. It's in an eccentric orbit, which is quite interesting for a lot of the work that I do, because it goes from being very close to the sun to not that close, and that actually matters for some of the CME observations that I make. It has a tenuous exosphere, so no atmosphere. The exosphere is very tenuous. Hardly liquid core, and this global dipole magnetic field that's actually offset northward from the center of the planet, which was an interesting Messenger result. And Messenger was launched in 2004, and it started orbiting Mercury in 2011, so it took a while to get there. And the mission went until 2015, when it was a planned crash into the planet. And of course, the reason for crashing it as opposed to just letting it fly around was that we got great data as it was going down. The last even few minutes of data was very valuable. So these are some of the science instruments on Messenger. I really just worked with the magnetometer and this energetic particle spectrometer, but there were a number of spectrometers to measure the surface composition, to measure the exosphere, and of course imagers to take nice images of the planet. This was what Messenger's orbit looked like. So this is pretty important for a lot of the work that I do, is that you can see that we're very close to the planet in the northern hemisphere, but really far in the southern hemisphere. So this is about 10,000 kilometers. And it had about an 8-hour period, well, 12 to 8 hours, depending on which year, as the period was lowered later in the mission. But it meant that we got to about 300 kilometers altitude. Well, actually, the lowest we got was about 20 kilometers altitude before the crash, which was really great. Some really useful data came out of those observations, actually. And so the fact that it had this highly eccentric orbit around Mercury means that we were actually able to observe both the magnetosphere and the solar wind. And that means that a lot of my research is actually possible. It wouldn't have been possible otherwise. So this is Mercury's magnetosphere. The key thing to note compared to what we saw for Earth's magnetosphere is that it's a lot smaller. This is because the strength of the global internal field is about 1% of the strength of Earth's field. So that means that the magnetic field is not able to stand off the solar wind to a very far distance compared to what Earth's magnetic field is able to do. And so here's essentially solar wind, interplanetary magnetic field on this side, and then on this side is dominated by the planet's magnetic field. And so just for reference, this distance, essentially from bow shock to the planet, is less than 2 Mercury radius. No, well, actually, sorry, that's 1 Mercury radius here. Slightly less than 1 Mercury radius. So it's very close to the planet. And because it's such a weak magnetic field, and we have this close distance to the sun, where we have high solar wind density and strong interplanetary magnetic field, what ends up happening is that the magnetosphere of Mercury is highly dynamic. So it gets distorted substantially if there are extreme conditions in the solar wind, especially such as CMEs. So I'll focus in on the bow shock, the magnetopause, and the cusp regions for my research, as these regions are essentially the boundaries of the magnetosphere, and the disruptions and changes in them will essentially indicate how things change inside in the very interior of the magnetosphere as well. So just a little bit about what a bow shock is. Essentially, as the solar wind that's supersonic is coming towards the planet Mercury, as it encounters the obstacle of the planet's magnetic field, it has to slow down. So it goes from a supersonic to subsonic state, and at that point, a shock front forms, and that's the bow shock, or shock wave. And behind that shock wave is what's called a magnetosheath, where you have this compressed, heated plasma bunched up right behind the bow shock, and flowing around what's called the magnetopause. And the magnetopause is this pressure balance between the planet's magnetic field and the interplanetary magnetic field and the solar wind's dynamic pressure, essentially. And there are currents set up on the magnetopause that end up canceling in certain regions the planet's magnetic field. And so this particular region, the cusp region in the north and in the south, the planet's magnetic field is highly weakened in that area. So that's where you have this cancellation of the planet's magnetic field. And in Earth's magnetosphere, that's essentially where the aurora happen. That's the polar caps, as we call them, at the Earth. That's where most of the energetic particles can come into the magnetosphere and cause the aurora. At Mercury, there is no atmosphere, so there won't be any aurora. But we still have high energy particles getting into the magnetosphere from the solar wind at these regions, even without having any extreme solar wind conditions. So just to show you for reference what CME actually looks like. So here's our average orbit in the magnetic field data around Mercury. So this is essentially, as we're getting close to the planet, we get a peak because we're getting close to the surface where the magnetic field strength is the highest. And then as we're getting further away in our orbit, magnetic field drops, and now out here we're basically out in the solar wind. So this is solar wind observations here. This is planet Mercury here. Now, this is what happens when you see a large CME. The entire observations are completely distorted. This is the CME arrival here, and our planet's magnetic field is completely distorted. The tail region, so, whoops, here, this part of the magnetic field, which was much lower, you can see this is the tail before. Here it's, 3 times the size that it was previously. So huge changes occur during CMEs, or can occur during the CME. So I put together a list or a database of all the CMEs that we observe at Mercury. And then I essentially looked at how the CME affects Mercury's magnetosphere during all those cases. So how, on average, CMEs are affecting the magnetosphere. And first order expectation is that during on average, during CMEs, because we have increased solar wind density and speed in the CME shock and sheath, we expect the magnetopause to move much closer to the planet and potentially even blow the magnetopause or in the magnetosphere away. So if you have, because we're in a weak magnetic field regime, and because the solar wind is so much stronger and CMEs are so much stronger close to the sun, we can expect that Mercury's magnetosphere might actually completely be pushed down to the surface of the planet. Now, during the Messenger mission, we actually didn't observe this. We never realized that we did observe such an event, and now I have actually found one of these events, and unfortunately I can't show that yet. But we have actually now observed a particular event where this CME pushes Mercury's magnetosphere completely down to the surface. And that's actually interesting enough in the sense that that's never been observed at Mercury or at any planet in our solar system. Now, we can also expect, because during in the magnetic cloud portion of the CME, the alpha Mach number is quite low, the alpha Mach number being given by this equation here. So this is the solar wind speed divided by the alpha speed, and this is ram pressure in the solar wind, and this is the magnetic field strength of the IMF. So essentially, from this relation, we can get that. So that particular Mach number is very low in the solar wind, in the magnetic cloud portion of a CME, which controls how close the bow shock is to the planet.
Rika, could you please say again what the dA is in the denominator there?
dA is the alpha speed.
The what?
Alphane speed. It's essentially it's a wave speed in the plasma. So
Okay.
you could have, so this is the Alphane Mach number. You could have a sonic Mach number, which would be the just the sound speed traveling through the medium. So this would be, solar wind speed divided by the sound speed through the medium if you had a sonic Mach number. This is an Alphane Mach number, so it's a different information speed, a different wave speed in the plasma. That matters for, specifically for magnetic fields. So I'm gonna just go through this and show you, essentially, this is what the bow shock looks like on average under normal conditions in the solar wind and the megapods at Mercury. So this is before CMEs, this is without CMEs. I built a probability density map. So essentially, these are the darker red and yellow regions are where we most likely observe the bow shock in space around the planet, and this is the megapods. And you can see that there is essentially a pretty nice, fairly narrow region, especially for the megapods, where these boundaries are actually observed on average. And some of these equations, you don't need to, you can ignore that, but essentially that's just the fit of this particular, the best fit line through the highest probability regions.
Could you please explain what those vertical lines are then? Are they a series of observations?
So they come from a series of observations, but what I did was I split the data. So if you just take the observations in space around the planet and you split it into essentially just cubes around the planet in 3D space, what we do is we find how often each portion, so each of these little cubes as we grid the planet, how often each of those little grids is going to get an observation of the bow shock. So if you get a lot of observations of the bow shock, like in here, that means that the bow shock is most likely to be there. If you're out here, where it's blue, it means that we've observed it probably once in that area. And in the white space, we've never observed it. So essentially, this is showing from lowest to high probability where the bow shock is likely to occur based on the observations that we actually made of where the bow shock and megapods are. And so this is now during CME conditions. You can see that there's a lot more variability. We have a lot less observations during CMEs. There are, about, how many? 60. So I actually gave them, oops, the other way. I gave a number here. So we ended up getting about 200 bow shock observations and 200 megapods crossings during CMEs, whereas we had, so to make this plot, we've had about 4,000 or 5,000 observations. So it's a lot less data that we have. Of course, CMEs are not happening all the time. So the statistics are certainly poorer. However, we can still make a fit to the observations. And so the nominal solar wind curve from this, so from this graph, I plotted the curve over there. So that's the blue one. That's from the time of average solar wind conditions. And same for the megapods. And then during CMEs, you can see what, that's the red curve, what we have during CME observations. And so what you can see is that during the bow shock is a lot more flared and further from the dipole, so further from the planet over here. And the megapods is a lot closer to the planet during CME conditions than otherwise, which is essentially what we expected. So that's a pretty nice result. And then, now the main result, I think, from this particular part of the study is that we actually find that the megapods of Mercury reaches the surface of Mercury on about 30% of CME affected cases. So that means that about 30% of the time that we have CMEs, there is no magnetosphere. Mercury's bayside magnetosphere essentially goes away. And that's just because the pressure of the CME in terms of the ram pressure, and because of the reconnection between the day side magnetopause and the CME, they can completely either compress the planets, compress the magnetosphere down to the surface, or actually peel it away. And so most of the time, so if there are no CMEs, we see this kind of thing occurring about 4% of the time. So CMEs are much more effective at essentially compressing Mercury's magnetosphere down to the surface than just the regular solar wind is. And this is largely due to the fact that we have a much higher dynamic pressure in CMEs than in the solar wind, since the speed of CMEs is a lot faster and the density is a lot higher. And so just briefly, I'll also go through how Mercury's cusps are affected by CMEs. This is because, so the cusp regions, as I mentioned, we care about because the field is weakened in that area, so we can get high energy particles coming in through the cusp, higher chance of the plasma actually reaching the surface of the planet and causing space weathering of the surface. So essentially the high energy particles can sputter particles from the surface into this to actually populate the exosphere of Mercury. And CMEs certainly have a high influence on this region. So what we mapped out was the cusp region. So this is, if you look down at the North Pole of Mercury, so picture looking down at the North Pole, that would be the center of this plot here. Sorry that these, the grid is not showing up very well there, but essentially this is the center of the North Pole here of Mercury. And the center of the North Pole in these pictures would be here. So in these images, this is under nominal solar wind conditions, meaning no CMEs are happening. You can see that these are observations, so these are our cuts, the messenger tracks through the cusp region, and that's what's shown over here as well. And the main thing to take away from this figure is that we see the cusp over a much larger longitudinal or azimuthal area than if there is no CME. And in terms of the latitude of how far the cusp extends in latitude is quite a bit further, about I believe 20 degrees higher. So what that means is that essentially if you picture at the Earth, we have aurora. Most of the time we see the aurora high in the northern latitudes. Now if you have a large CME, you end up having the aurora extend much further in latitude south, right? So for example, if you've heard of the Carrington event, which was the largest CME that was actually ever observed at the Earth, the aurora, as far as I remember, went down to even Mexico. So just huge latitudinal extent for that particular CME event. So that's what this is essentially the equivalent of. We see that the cusp actually, or the aurora equivalent at Mercury extends way further south during CMEs than on average. And we also observe a lot more particles actually hitting the surface in that region during CMEs than during normal solar wind conditions. So about an order of magnitude greater flux to the surface of high energy particles are occurring during CMEs. And this is just another quick example of a very strong CME hitting Mercury. You can see this particular CME completely distorted the planet's magnetosphere and then continued to do so for another number of orbits. And this particular CME also caused a giant cusp in the magnetic field observation. So this is an observation of the cusp region, which would be around here, and you don't see anything. So this is where you don't see a cusp, and this is where we have this giant cusp, this big depression in the magnetic field. So just to show that CMEs can do some pretty big damages at different planets. And so that just wraps up that essentially. So just in Okay, I don't have too much time left, but in about 5-10 minutes, I'll show you a little bit about how galactic cosmic rays are affected by CMEs. So galactic cosmic rays, just for a little bit of an introduction, are particles that are generated outside of our solar system, likely in supernova explosions. Their peak flux, as they're observed near the Earth, is in the hundreds of MeV. So they're very high energy particles. They're largely dominated by protons. About 90% proton, 7 to 10% helium nuclei, and then the rest are higher isotopes. But the point is that they're coming through our atmosphere all the time. They're going through all of our solar system all the time. And what we see is that CMEs are actually able to modulate and change the flux of these particles, and actually cause them to drop in the flux of these particles as a CME goes through. So these are called Forbush decreases. We've observed them in different places in our solar system. They're short-term drops. So let me just get to that figure to show you quickly what they look like. So this, for example, the red here is showing the GCR flux, so the galactic cosmic ray flux at Mars. And you can see that there's this huge drop in the galactic cosmic ray flux as the CME is going through. This is the time the CME arrives, and then there's this drop in the flux, so a change in the flux as the CME is going through. And what's causing this drop in the flux is, first, there's a drop in the flux at the shock and the sheath of the CME. It's caused that's due to some changes in the diffusion coefficients of the particles that happens at the shock, and also because of the closed field line geometry, the closed magnetic field portion of the CME, we also see a drop. So essentially, the magnetic cloud portion or the flux rate portion of the CME, because it's a little magnetic bubble, or not little, a large magnetic bubble, it's able to deflect these high energy particles, or at least a large portion of them, from entering that region that the CME is dominating. So as these CMEs are going through, they will have a large effect on the GCR population in that environment. So I'll show you one particular CME that was, and show what it did to the galactic cosmic ray flux at different locations in the solar system. So this particular CME, this bubble here, is the CME. And this bubble over here is the CME here in these simulations. So you can see that the CME is leaving the sun, it hits Mercury, then it comes out, it also keeps going and hits Venus and Earth, and keeps going and hits Mars as well. In this particular CME, so as it went out, it hit all the inner solar system planets, and we actually had observations of the galactic cosmic ray flux at Mercury, Earth, and Mars. So other than Venus, we've had observations at all of those locations for this particular event, which was really nice. It's never been the case before. We've never had 3 locations to observe the GCR flux for a particular CME. So the fact that we have all these spacecraft is a huge asset for the research that we do. So at Mercury, you can see the black curve here is showing the GCR flux. And as the CME arrives here, you see that there's a large drop in the flux, and then it recovers sometime later. At Earth, I'm showing it in blue here. You can see the large drop in the flux as the CME arrives and then recovers later, and the same occurs at Mars. So it's interesting that this is shown in the normalized plot, meaning that these are relative, that we can actually compare the drops between the different planets. And what's interesting is that we have a 15% decrease in the GCR flux at Mercury, about a 9% decrease at Earth, and about a 6% decrease at Mars. So as the CME is going through, it modulates galactic cosmic rays differently at different locations. So the CME is getting weaker as it propagates further out, and it's actually able to it's not able to shield the region from GCRs as much as it was close to the sun. That's the main takeaway from that. So by looking at these observations at the different locations for this particular CME, we see that the Forbush decreases, or these drops in the flux, are steeper and deeper closer to the sun. They also last a shorter length of time because, of course, the CME is smaller close to the sun than further out. And it seems like the magnetic field strength in the CME is the one that plays the largest role in actually modulating these GCR particle fluxes. So I'm actually going to start with the conclusions for this particular one, is that we can make a hypothesis for the upcoming missions, the Parker Solar Probe in Europe. There's a European planned mission, the Solar Orbiter mission, that's upcoming as well. That's going to go close to the sun. We can make a hypothesis for these missions that they're going to observe much stronger CME-driven modulation or changes in the GCR flux as they go closer and closer to the sun, because the CMEs are much stronger closer to the sun. And yeah, finally, the main conclusions for the talk are that CMEs have a large effect on, as I showed, through planetary magnetospheres and different planetary environments, as well as they can change significantly as they're propagating through the solar system. Thank you very much.
Thank you very much. Do we have some questions from the floor? Chris?
Well, first, a statement. The next transit of Mercury is November 11th next year. And it'll be happening at sunrise. So I'm sure if the weather cooperates, which is certainly not a given at that time of year, there'll be somebody around looking at it.
I should definitely make sure to keep it in mind.
Yeah. Next one after that is not until 2032. So
you better set your alarm.
Now, the European mission you were mentioning, is that Bepi Colombo, is that what you're talking about? Or?
Bepi Colombo is going to Mercury.
That's going to Mercury, and that's going up in a few weeks. Are you?
I'm not part of that mission, no. That's a European based mission, but the one I mentioned was Solar Orbiter, and Solar Orbiter is going to try to do something similar to Parker Solar Probe, but not get it quite as close. But they will end up having, I think, more years of observations in the end for Solar Orbiter.
Yeah.
So it's more of a heliophysics mission than Solar Orbiter, whereas Bepi Colombo is a planetary mission, specifically to go to Mercury.
Will it be providing any useful data for you?
I hope so. Yes, definitely. The issue with, of course, accessing data for different countries, that's not always as simple. So with Parker Solar Probe, NASA has this requirement that, well, with all NASA missions, the requirements are that about 6 months after the data is available, it has to be made publicly available, so anyone should be able to access it. Not all institutions and agencies have that kind of requirement. So I'm sure the Europeans will release the data, but it's harder to, for example, get data from the Chinese missions.
Right. John?
This is probably a stretch, but the sputtering that occurs at the cusp of Mercury during the CME, in principle, changes the surface a little bit.
Yes.
Is there any possibility that one could observe that visually?
We tried.
You tried?
We tried. It's a very good question. No, not really, no. So you can see something called reddening of the surface.
I just wondered because, over it kept happening year after year for a long time.
So here's my unofficial take on this. Mercury's magnetosphere it just lets in particles all the time. I think that most of Mercury's surface has been sputtered to death. And so certain regions, one of my main topics and questions when I was doing my PhD was actually exactly that. Are there regions that are more weathered than others due to this high energy particles reaching it? And it turns out that a lot of my research pointed to the fact that yes, we have a lot of sputtering in the cusp, and yes, we have then a lot of sputtering in the southern hemisphere because the magnetic field is even weaker there. So it ends up being so many pockets of the surface having a lot of sputtering, plus you end up putting in CMEs that completely ram the surface, the magnetosphere into the surface, and you don't end up having even a magnetosphere at all. And now you have this huge energetic particles reaching the surface. That overall, over billions of years, I think that surface has been essentially sputtered to saturation, that you wouldn't see a difference.
Thank you. Yes, sir.
At the beginning of your talk, you mentioned the prediction process, which is not too good because you can't predict the speed of the CME sometimes, particularly with Earth. So what kind of predictability do we have at the moment, say, for a major CME that might cause problems? Or do we not?
We have. We have predictability, but so the key things that are still a big question currently are the speed of the CME and the magnetic field direction of the CME. The speed changes quite a bit as the CME leaves. So we can have an idea of what the CME speed is at the sun, but then as it reaches the solar wind, it slows down. And how it slows down and exactly what the relationship is, it's not yet quite clear. And the magnetic field direction is not clear at all yet. So we can say within about 12 hours if the CME will arrive or not. So that's pretty good. But in terms of whether it's going to cause a geomagnetic storm, at this point, it's pretty much up in the air. If you see a really, really high-speed CME at this point, then we can say, yes, that will most likely cause some sort of storm. But if it's just your average CME speed, we can't really tell. But there are a number of, there are many models that are being worked on in terms of both magnetic hydrodynamic simulations and various others that try to make predictions. And also a number of US government websites that do have predictions and forecasts and, available. One is the Integrated Space Weather something, ISWAP is the acronym, if you want to look that up. It actually gives you some really nice figures and movies of CMEs actually leaving the sun and then projecting them out further into space and how they travel and trying to make predictions. So how accurate these are, it's not that great yet, but we're making progress.
Well, I've got a few questions. One, with a 1% magnetic field of the Earth, when they sent messenger, did they know it had a magnetic field?
Yes, we knew that it had a magnetic field, although it wasn't still clear until essentially there were a few flybys that we didn't know whether it was a global magnetic field or not. We knew that there was a magnetic field, but it wasn't clear whether it was a globally generated internal field. So that was confirmed after that.
And so you mentioned that it has a liquid core. It would have to have a liquid core to generate the magnetic field.
Yeah.
Mercury, Venus instead, it does not have a magnetic field, does it?
No, it does not.
So it's solid.
Yes.
Now, Venus, I understand, does not have plate tectonics. So it's not got a churning under surface.
So you need to have convection in the core in order to.
Does Mercury have any evidence of plate tectonics?
Good question. No evidence of plate tectonics, but there is evidence of essentially the planet cooling and shrinking. So as it's cooling and shrinking, it will have cracks on the surface. But there is no plate tectonics on Mercury either. So the plate tectonics more is required than just what you would need for to generate a global magnetic field. I don't know if, as far as I know, those conditions were not factored.
Thank you. Now, Sherry Butner, our past president, is an Aurora evangelist, and she was very excited that she heard you were going to be here, but unfortunately she could not attend. And this might be outside of your expertise, but she was interested, if you have any explanation for this thing called Steve, which is a weird...
Yeah, I've never heard of it, so
You
I
haven't
certainly
heard of it?
don't.
Okay. So maybe we'll talk about it offline.
You'll have to tell me about it.
Are there any other questions? Okay, well, thank you very much, Rika. As a token of appreciation, we have a coveted t-shirt from the Victoria Center of RASC for you, and we have it in a variety of sizes, so we'll sort it out. So if you want, you can change it. And thanks again for sharing your expertise and passion, and I think you made us realize it's a pretty complicated world for magnetism out there, and I found it very interesting. Okay, thank you very much. And afterwards, please join us in the 4th floor of the Elliott Building for tea and coffee and cookies. And if the people are interested, I have a few more hard copies of our Sky News newsletter.